My name is Wei-Jia. Today I will talk about Joule heating at high latitude using FPISR measurements. Here is the outline of my talk. First, I will give some background information and motivations to do this study. Then I will introduce data and methodologies. After that, I will present the results specifically on statistics of Joule heating and the effects of electric fields and neutral winds. At last is a summary. Let's move on to the first part. Joule heating is an important way through which energy is transferred between ions and neutrals in the ionosphere. So, to study Joule heating can help us understand the coupling between ionosphere and thermosphere. However, statistical studies of Joule heating rates has been done with only limited data sets. So, the linearly continuous FPISR radar measurements make it possible to estimate linear growth rate, to estimate Joule heating rates, and analyze the effects of electric field and neutral winds in almost a solar cycle. Here is a brief introduction to FPISR radar. FPISR is an advanced modular incoherent scatter radar, which is a monostatic electronically steerable phased array radar that is capable of beam steering on a pulse basis. Most of the measurements used in studies from IPY mode, which is an effort to make nearly continuous observations over a solar cycle. In this study, I followed the method used in Say's paper to calculate the total Joule heating and local Joule heating. The total Joule heating includes the effect from neutral winds, and the local Joule heating assumes the neutral wind to be zero. The electric field and neutral wind can be estimated from measurements of line of sight velocities of ions, and Peterson conductivity can be calculated with inertial densities. For this study, 86 measurements from February, March, and April in 2012 are collected. These measurements cover the region between 90 kilometers and 130 kilometers with 5 kilometers resolution. The time resolution is about 15 minutes. To avoid the effect from low quality data, a threshold of signal-to-loss ratio is applied, which is -20 dB. Also, to avoid the effect from outliers, a rounding median filter with 1 hour window is applied to all parameters. At last, all the measurements are divided into two subsets corresponding to quiet and active conditions, respectively. Here, quiet condition means AE index is less or equal to -20, -200 NT, and active condition means AE index is over 200 NT. Let's move on to the results. First, I want to show you an event on February 13, 2012. Here, the first panel shows the variation of AE index and also the measurement of electric field of geomagnetic field from a local magnetometer. The second panel, these measurements indicates that the condition in the evening and post-midnight sector is disturbed. Then the second panel shows the variation of electric density as a function of height and MLT. We see strong enhancement of electric density in the evening and post-midnight sector. Then the third and the bottom panels shows the local and total Joule heating. The fourth panel shows the integrated Joule heating rates. Let's first see the result in the integrated Joule heating. We see that during the daytime, local and the total Joule heating are both very weak, and total Joule heating is much larger than the local Joule heating. But in the evening and post-midnight sector, these two Joule heating rates are increased, and especially in the evening sector, we can see that the local Joule heating can exceed the total Joule heating at some moments. That indicates that during these moments, the electric field can work to accelerate the neutral winds, and in this way, the neutral winds decrease the total Joule heating. The integrated Joule heating terms can give us a net result, while the height result information will give us some vertical distribution of the Joule heating. From the third and bottom panels, we see that enhancement of Joule heating appears only mainly about 100 kilometers in the evening and post-midnight sector, and about 110 kilometers during the daytime. Then let's see the neutral winds and electric field in this day. Here, F and G shows the zonal and the meridional neutral winds. H shows the electric fields. The most obvious feature we can see is that the meridional neutral wind enhanced during the evening and post-midnight sector, and also we see enhancement in the meridional neutral winds in the evening and post-midnight sector. So this might indicate that the strong Joule heating enhancement in the evening and post-midnight sector could be associated with enhancement in meridional neutral winds and electric field. Then let's see the statistical results. First, let's see the recursion rates. In this study, I calculate the count of the recursion in this way. I first count the total measurements in each grid, and also count the measurements that above a threshold. Then I calculate the frequency, the recursion rate for each term. Here on the left it shows the result under quiet condition, and on the right it shows the result under active condition. From the result in the left two columns, we see only weak occurrence rates in the evening sector and very close to zero occurrence rate in the post-midnight sector. But on the right columns, we see strong occurrence rate in the evening and post-midnight sector, and the occurrence rate in the evening sector are stronger than in the post-midnight sector. Also, we can see that the occurrence rate of local Joule heating is a kind of larger, is a little larger than the occurrence rate of total Joule heating. Then let's see the strengths of Joule heating. Here, the first again, the left column shows the result under active condition, quiet condition, and the right column shows the result under active condition. The first panel shows the result of local Joule heating, and the bottom panel shows the result of total Joule heating, and the integrated terms are shown in the middle panels, middle row is middle. From the integrated terms, we see that under quiet conditions, the total Joule heating and local Joule heating are very weak, and most of the time the total Joule heating is much larger than the local Joule heating, except in the evening sector when the total Joule heating when the local Joule heating increased. So this indicates that under quiet conditions, during most of the time, neutral winds tend to play a dominant role in Joule heating, but in the evening sector, electric field can play an increased role in generating Joule heating. Then on the right panel, we see that during the daytime, the local Joule heating is still, the local and total Joule heating are still very weak, but in the evening and the post-midnight sector, these two terms, the total and Joule heating, both increased a lot, and we see that total Joule heating could be close to the local Joule heating is almost the same range. This is almost the same value of as total Joule heating in the evening sector, and we can see that the peak of the total Joule heating appears earlier than under quiet conditions. Then let's see the height result. We see that the enhancement of Joule heating mostly occurred about 110 kilometers. Then let's see the effects of electric field and neutral winds. Here we defined two terms. one is for hydro reserve turns and one is for integrate turns. The ratio R equals to the difference between local Joule heating, total Joule heating, and divided by total Joule heating. This ratio indicates the effects from electric field. So when this value is large, which indicates that the electric field play a increasing role in Joule heating. When this term is very small, which indicates that the total Joule heating comes mainly from neutral winds. Okay, let's see the result on the left column, which corresponding to quiet condition. Let's see the integrated term. Here we see that during most of the time the ratio is around minus 20%, which indicates that most of the Joule heating results from neutral winds. But in the evening sector, the ratio is around minus 50%, which indicates that the contribution from electric field and the neutral winds are comparative. From the hydro result, we can see that during most of time the enhancement larger ratios appears in around 110 kilometers, but in the evening sector, larger ratios appears in a larger range. Then under active conditions, we see that the ratio is large in the evening and in the post-midnight and the evening sectors. And in the evening sector, we can even see positive ratios, which indicates that during this period, the electric field can accelerate the neutral winds, and neutral winds tend to reduce Joule heating. And also from the hydro result, we see that in the evening and post-midnight sector, large ratios appears in a larger range, and during the daytime, large ratios appear in a narrow range around 110 kilometers. At last, let's see the relation to electric fields. As we have already seen in the case study, that total Joule heating enhancement is mainly related to meridional electric field and neutral winds. So we will only care about the meridional electric field. Under quiet condition, we see that during most of the time, the electric field are very weak, and only in the evening sector we see some enhancement of meridional electric winds. This might indicate that correspond to the enhancement of Joule heating in the evening sector under quiet conditions. Then let's see the result under active conditions. We see enhancement of meridional electric field in the evening sector and also in the post-midnight sector. The maximum enhancement appeared around 18 local time, which is much earlier than what we see in the under quiet conditions. So the maximum enhancement in the evening sector is a kind also larger than the enhancement in the post-midnight sector. So this might be related to the larger enhancement of local Joule heating in the evening sector. Last is a summary. Our case study indicates that Joule heating enhancement is closely related to disturbed AE conditions, and also suggests that neutral winds play a dominant role in increasing Joule heating during quiet period, while electric field play a dominant role during active period. And case study suggests that Joule heating is closely associated with meridional electric field and meridional winds. Our statistical results indicate that under quiet condition, neutral winds play a dominant role in increasing Joule heating during most MLT, except in the evening sector. Under active condition, Joule heating enhancement increases in the evening sector and post-midnight sector when meridional electric field enhance. Under active condition, neutral winds could even reduce Joule heating by a maximum rate of 25% in the evening sector. Thank you. That's end of. Here's some references.